Okay, so this last part of our unit is on nuclear chemistry, and specifically, it's about 3 types of radioactive decay: alpha, beta, and gamma decay, and how they change the nucleus. Specifically, how they change the number of protons that are in the nucleus for the most part. These different types of radiation can have different amounts of damage if you happen to be in the wrong place at the wrong time. And so we'll also see how we would rate one versus the other. When we look at a particular isotope of any element, we see, of course, its symbol, its abbreviation. This would be for uranium. And then there are 2 numbers associated with it. The bottom number is representative of the atomic number. It literally tells you which element you're looking at. However, sometimes for some of our particles, instead of representing the atomic number, it will represent the charge. Now, for most elements, this would be the same thing because we're talking about basically how many protons are in the nucleus, and they could also be looked at as what's the charge of just the nucleus by itself. The top number is called the mass number, and the mass number is made up of protons and neutrons. Here are examples of the 3 types of radiation. First, we have alpha production or alpha radiation, which is basically a helium nucleus. So it's a helium atom without its 2 electrons. So we could also think of it as being an ion, a +2 ion, because it has lost both of those electrons. We have beta production or beta particles, which essentially are electrons. So the nucleus is sending out an electron from inside. Now you might say to yourself, well, wait a minute, electrons aren't in the nucleus. And that's true. Electrons go around the nucleus, but what actually happens is a neutron turns into a proton and an electron. It splits apart. The electron gets sent outside the nucleus. And then we have gamma ray radiation, which is the most energetic, the most dangerous, the one that needs the most protection from. One of the things I'd like you to focus on when you're looking at this screen are the numbers. And there's a very simple rule, very similar to what we were doing with our balancing chemical equations. Remember I said nothing can be lost, nothing can be gained, everybody has to go somewhere. Well, the same thing has to be true here. So when I see that 238 there for the mass number, that's basically the mass of the protons and neutrons. And it's going to turn into these 2 things. Well, I can't have a different mass number altogether. It still has to be there. So if I add up the 2 numbers, the 4 and the 234, they have to add up to equal that 238. Likewise, the same has to be true on the bottom for the atomic number. Here I have helium with its 2 and thorium with its 90. 2 and 90 equal 92. Even with the beta production, note that on the bottom, 91 subtract 1 equals 90. Whereas on top, of course, 234 plus 0 equals 234. We will not be doing much balancing when it comes to gamma radiation because with both of them being 0, no charge and no mass, basically just a high energy photon, then there's no point to the balancing. It's not going to change anything. Basically, when the number of neutrons and the number of protons is about the same thing, and therefore their ratio is about 1, way down here, the very lightest elements, for the most part, they're not radioactive. They don't decay. But as we get further and further down on the periodic table, as the elements get heavier and heavier, and this ratio between the neutrons and the protons gets away from 1, we start to have certain types of decay. And so in this range, we have the beta decay, and then we get alpha decay later on. That decay is pretty much just to make it in a more stable form. Now, alpha decay is very limited to large nuclei, such as those in the heavy metals. And when we're saying heavy metals, basically we're saying the metals that are like in rows 6 and 7 kind of heavy metals. Beta decay converts a neutron into a proton. Literally, a neutron is an electron and a proton fused together. Well, going in the opposite direction, that neutron broken apart, the neutron turns into a proton, which means the atomic number goes up by 1, and that electron is sent outside of the nucleus in the form of beta radiation. This is probably the one thing I would focus on, this one page, more than anything else. There is also a table like this in chapter 25 that says pretty much the same stuff. This is like a dozen questions on the test, just off of this one page. First off, you need to recognize the symbols for the different types of radiation. What an alpha symbol looks like, a beta symbol, or a gamma symbol. Also, their alternate forms. In other words, not only do we have the alpha symbol with the A, but an alpha particle is the He, 4-2 with the 2 plus for its charge. Not only is a beta particle with this cursive B, it's also an electron. For the gamma, that's just a high energy photon. We don't have a second symbol for it. In terms of their mass, basically all we care about is in relation to each other. The alpha particle is the heaviest, light particle for the beta. The gamma has no mass. This middle part is really the most important thing to keep straight. What does it do to the nucleus? Well, when an element has alpha radiation, basically it decreases the mass of the element by 4, and it decreases the atomic number by 2, so it literally turns into something else. On the other hand, beta emission converts a neutron into a proton, so the atomic number goes up by 1, but since neutrons and protons pretty much have the same mass, it does not change the overall mass of the element. And then gamma ray has energy related to it, but it does not change the mass, and it does not change the atomic number. Hence, both those are zeros. In terms of penetration, again, all we really care about is which ones penetrate the most, means can go through other things. Alpha particles being the biggest and heaviest have low penetration. Beta particles, modest penetration, and gamma rays pretty much go through everything. In terms of protection, your skin is pretty much enough to protect you from alpha particles. You could be damaged if you swallowed something that was sending off alpha particles, but otherwise you're pretty much okay. Paper, clothing, aluminum foil are more than enough to protect you from beta particle radiation. Gamma, you need basically a lead shield of some kind. Probably remember going to the dentist and wearing that heavy vest. It's lined with lead to protect you. If it's not lead, you basically need several feet of concrete to stop gamma radiation. So the highest penetration needs the most protection, and of course it is the highest danger. So we worry more about gamma ray radiation in terms of being dangerous for you than we do about alpha particles. Now, another thing to keep straight is that where electrostatic forces are things that keep positive and negative ions together in a crystal, it is nuclear forces that keep protons and neutrons together in the nucleus. So nuclear with nucleus. Because just like electrons repel other electrons, protons should repel other protons. Things of the same charge repel each other. Well, something has to keep them together in the nucleus, and that is the nuclear force. And then you also need to know a little bit about fusion and fission. And so we have some diagrams to help out. Here is an example of a fission. Basically, we are taking a heavy element and we are splitting it into smaller pieces. And so you could have a chain reaction of these things, such as you see here. The U-235 gets broken apart by the radiation and keeps breaking apart into smaller and smaller pieces. That is nuclear fission. A certain amount of energy is produced with fission. Fusion is the opposite. Fusion is bringing small particles together, light particles together, and fusing them to create a bigger particle. And for example, this is how helium is created. It's basically the joining of 4 hydrogen atoms into 1 helium atom. It does not occur in one step. It takes several steps to do so. And in fact, in the picture that you're looking at here, you see the heavier forms of hydrogen, H2 with 1 proton, and H3 with 2 proton, or H2 with 1 neutron, and H3 with 2 neutrons, whereas most of the hydrogen in the universe doesn't have any neutrons. And when we combine them, we make the heavier elements. Put a couple of heliums together and you can create carbon and so forth. It takes a supernova, however, to create the really heaviest elements. So again, you are merging or fusing things together to produce bigger things. Now, if you were to take 4 hydrogen atoms and add them up mass-wise and compare them to the mass of a helium atom, it wouldn't exactly match. The reason they don't match exactly is some of the mass, which we call the mass defect, has actually been converted into energy according to Einstein's famous equation, E equals mc squared. The little triangles stand for change in, and so the change in mass, which is called the mass defect, basically gets transformed into a change in energy. C is for the speed of light. The speed of light is 3 times 10 to the 8th meters per second, or 300 million meters per second. This is c squared, and so when you square it, you're basically talking about a multiplying factor of 10 to the 17th power, which even if the delta m is a very tiny amount, like 2 or 3 decimal places, when you then multiply it times 10 to the 17th, it's still a huge number. If we wanted to make a comparison between, say, burning coal and fission and fusion nuclear reactors, well, this number here, 3.3 times 10 to the 7th, that's about 33 million. Notice that this is 10 to the 12th and 10 to the 14th. So this is 100,000 to 10 million times the amount of energy that's being produced. Not to mention, look how much higher the temperatures are when you're talking about nuclear fusion. This is, of course, what goes on in the middle of stars. Literally, when a star burns up its hydrogen, it's converting it into helium and the heavier elements. And then here is a little schematic of a fission reactor. This is how we generally produce energy from nuclear power plants. We break them apart. The bigger things like uranium and plutonium, we break them apart. We have fuel rods. The fuel rods need to be cooled by water. And of course, if anything interrupts that cooling process, such as the earthquake that Japan faced a while back, damaged the ability of the reactor to keep the fuel rods cool, and that's what led to all the radiation problems for the local community.